Hello and welcome to the Daily Space. I'm your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we're here to put science in your brain.
On a very non science note, yesterday, February 2nd, a groundhog saw its shadow and we get 6 more weeks of winter. As a scientist, this whole holiday is the height of silliness. Winter lasts another 6 weeks. That's just how it works. And it's why Pamela is cold in her studio.
But science can be fun too. And despite being very cold, I am brought great joy by looking at robots being operated from space and helicopters on Mars that could glow in the dark, which is awesome.
We also look at how analyzing rocks here on Earth could help us find life on other planets. And then Eric will be here to tell us about the latest of several SpaceX launches this week and share what's up in the sky.
So let's get to all that science, shall we? Science is full of stories that sound nice and straightforward only because it is really easy to ignore all the exceptions to the rule. Consider earthquakes. As the story goes, earthquakes come from the motions of the crustal plates that carry around the Earth's land masses. Where two plates get stuck on each other, either where they plunge over and under each other or pass side by side, earthquakes can occur in the bad moment when those stuck plates get unstuck. This means, so the story goes, when we see quakes on the moon and Mars, we are seeing indications of a geologically active world and possible plate tectonics, unless the quakes are actually related to volcanism, or unless the quakes are caused by impacting asteroids shaking the world. Or, now we learn, quakes can be from land rebounding from past asteroid attacks. In new research looking at the Red Fort impact structure in South Africa, researchers have found evidence that the land around the structure continued to be shaped by the impact in new ways for millennia. Formed 2.02 billion years ago when a 10 to 15 kilometer across rock hit Earth, this structure has been eroding under the forces of weather ever since. This gives us a unique opportunity to see the subsurface structures in a crater, including impact melt dikes, places where melted rock made inroads into the surrounding material. In a new paper to appear in Icarus, researchers led by Matthew Huber look at compositions of these dikes and at the structures of other features and find they describe a prolonged period of unrest associated with the impact. The impact would have initially compressed the region it hit, and according to the paper, and I quote, deep fractures formed in the crater floor as the crust recovered from the impact. Melt dikes formed in multiple stages over an extended period of time. Crustal relaxation at the Red Fort crater lasted circa 1 million years. End quote. Crustal relaxation. That means that after getting compressed, the land rebounded back to a less compact state, and as it did, things shook. Melted rock flowed in bursts, and to quote Huber, even tens of thousands of years after an impact, you would not want to be building a house on the periphery of a crater. Well, the paper confines itself to discussing the one terrestrial crater. This is a reminder that as we look at Mars, we need to remember that rebounding land can trigger quakes. And Mars, well, it has rebounding lands.
With the Vredefort impact structure, researchers can readily hike out to the structures they want to explore and poke at them with scientific instruments. Making similar measurements on other worlds is possible, but it is becoming more and more apparent that the scientific poking around is going to be done by robots, not people. An article in the journal Open Astronomy discussed an experiment involving a rover driving around a hangar in the Netherlands. That sounds pretty boring, but the place where the rover was being controlled from was far away on the International Space Station, driven by ESA astronaut Luca Parmitano. The experiment Analog 1 was part of the Metron series of experiments. Almost all of the interplanetary missions to date have been done by robots, with the exception of the Apollo missions. Robots can go places humans can't go, but there's no substitute for a human geologist actually hammering some schist on the moon or Mars instead of the timid drilling of a robot. But that's not possible yet. The next best thing is having a human control a robot on another planet, possibly from orbit around that planet. That will be much safer than going there in person, and it will still allow better science to be done. However, there are some problems with this method, mainly how to provide feedback to the operator, which is basically the objective of Analog 1. Astronaut Parmitano successfully operated a rover from the ISS, driving the rover over a simulated lunar surface. In addition to driving it, he moved the arm on the robot up, down, left, and right and was able to feel the arm bumping into things as he moved it. Further, he could tell how much things weighed through a feedback mechanism. According to one of the paper's authors, Kettle Warmness, it is possible that this could one day even pave the way to establishing and sustaining a human presence on the moon.
And on Mars, at least, it looks like some of those remotely controlled devices just might glow. Mars is a dusty place, and new simulations find that tiny helicopters flying in the Martian air may build up charge on their propellers and casing. And according to research led by William Farrell, the faint glow would be most visible during evening hours when the background sky is darker. NASA's experimental Ingenuity helicopter does not fly during this time, but future drones could be cleared for evening flight and look for this glow. The physics behind this is very similar to the phenomena of rubbing a balloon on your hair or on a pet, and then using the balloon to either get hair to stand on end or to stick the balloon to a wall. Friction between the two very different kinds of surfaces can allow electrons to jump from one object to another. And this brings us to my favorite word in physics. That difference between surfaces is referred to as their triboelectric value. Cats have a very positive value, and balloons are more on the negative side of the series. And similar can be said of helicopter blades versus Martian dust. Here on Earth, when ships at sea enter storms, a charge can build up on masts. Same with airplanes in storms. We also see friction in ash and volcanic plumes build up charge. In all instances, this glow, referred to as St. Elmo's fire, often precedes lightning. On Mars, that isn't a concern. So I, for one, look forward to a future of tiny glowing helicopters flitting through the Martian twilight. But that is likely far in the future. For now, let's take a look at Earth's deep past and a history of oxygen and the life that made it and allowed life like us to come into existence. Stay tuned.
A lot of times in science, to understand where you are and what will be, you have to look back at where you came from. In the search for life beyond Earth, with our sample size of just one, we are compelled to understand everything we can about how life came about here on our pale blue dot. That way, we have some idea of what to look for on other worlds. It's not a simple process. Earth so far has proven to be unique, and we're not 100% certain just what ingredients were needed to allow life to not only develop but flourish. There are thousands upon thousands of known exoplanets out there, but we haven't found that perfect Earth 2.0 that will give us a possible sample size of, well, 2. So we look back into Earth's past to try and understand how life arose and maybe find a for something we can find elsewhere that will tell us, yes, that planet has life. In new research published in the Proceedings of the National Academy of Sciences, scientists analyzed the oxygen content of iron-rich sedimentary rocks from around the world, trying to understand what Earth was like in the distant past and what changes came about that we can maybe measure in an atmosphere elsewhere. Co-author Maxwell Lechte explains, until now, there was a critical gap in our understanding of environmental drivers in early evolution. The early Earth was marked by low levels of oxygen till surface oxygen levels rose to be sufficient for animal life. But projections for when this rise occurred varied over 1 billion years, possibly even well before animals had evolved. And that's where the rocks come in. These iron rich sedimentary rocks, or ironstones, provided the researchers with a way to determine the amount of oxygen present when the rocks formed. The results were intriguing, as lead author Changle Wang goes on to explain. These ironstones offer insights into the oxygen levels of shallow marine environments where life was evolving. The ancient ironstone record indicates around less than 1% of modern oxygen levels, which would have had an immense impact on ecological complexity. And Lechte continues, these low oxygen conditions persisted until about 800 million years ago, right when we first start to see evidence of the rise of complex ecosystems in the rock record. So, if complex eukaryotes were around before then, their habitats would have been restricted by low oxygen. So, how did Earth's oxygen levels increase dramatically enough to harbor larger and larger life forms? That rise is called the Great Oxidation Event, and it is thought to have been caused by cyanobacteria producing oxygen through photosynthesis. Of course, oxygen is toxic to life, so that same rise of oxygen probably caused a mass extinction event. No, really, oxygen is toxic. That's why we need antioxidants. It's slowly killing us. Biology is bizarre. I much prefer rocks. Now, all of this leads us to the search for life beyond Earth, because oxygen can be detected in an atmosphere from space. Our sample size of one may just be enough, if we understand it, to point to ozone as a biosignature in another atmosphere. Another co author, Noah Planavsky, notes ozone strongly absorbs ultraviolet light, making ozone detection possible even at low atmospheric oxygen levels. This work stresses that ultraviolet detection in space based telescopes will significantly increase our chances of finding likely signs of life on planets outside our solar system. And that's where that new shiny golden telescope comes into play. One of its goals is to look at exoplanetary atmospheres, which we can then analyze and use to hunt for possible biosignatures like ozone. I, for one, am looking forward to all of that research. Of course, to get to using space telescopes, we have to launch space telescopes, and not all of them are for science. Coming up next, Eric Mattis covers the latest SpaceX launch and then tells us what's up. Stay tuned.
On February 2nd at 2027 UTC, a SpaceX Falcon 9 launched the NROL 87 mission into orbit from Slick 4E at Vandenberg Space Force Base in California. Let's watch the launch. As is typical for NRO launches, no details about the payload were disclosed, and after the first stage separation, the webcast switched to exclusively following the first stage as it completed its boost pack, reentry, and landing burns to do a return to launch site landing under 400 meters away from the launch pad it had departed 8 minutes earlier. The lack of second stage coverage permitted the showing of the first stage from space all the way back to Earth, and without the usual cutout at landing since the pad was on land. After the first stage was safely landed, the SpaceX commentator signed off and the webcast ended. We can't cover an NRO launch without talking about the patch for the mission, as they're always unique and sometimes slightly terrifying. NRO 87's patch features a mountain goat on a peak with mountains and a starfield in the background. The NRO described the mountain goat's symbolism as, quote, standing proud on a mountain peak, remaining watchful alert. From one event shrouded in mystery and symbolism to one that's just a coincidence of flight lines, this week in What's Up is a conjunction of the moon and Uranus. This event is not particularly special. It's a coincidence of two objects happening to appear right next to each other from the perspective of someone standing on Earth. In reality, the two objects are billions of kilometers away from each other. Uranus will be within 2 degrees of the moon, less than the distance of two fingers held out at arm's length, this coming Friday, February 11th, in the early evening. You will be aided by the moon's relative dimness being in its waxing crescent phase. Unless you have a really large telescope, you will only be able to see Uranus as a dot, not a fully resolved disk, but it's still an interesting blue screen dot and bright enough at between magnitude 5 and 6 for even small telescopes. In a telescope at moderate power, you should be able to fit part of the moon and Uranus in the same field of view to see details on both simultaneously. While you're in the region, you can explore the moon's craters at high and other features at high power. Another close conjunction that recently happened was that of the moon and Jupiter. Jupiter was within 4 degrees of the moon, a bit less than 3 fingers held at arm's length, this past Wednesday, February 2nd, in the early evening. Jupiter is technically still visible, but it's very low in the horizon and sets shortly after sunset. Jupiter will be better positioned later this summer, closer to opposition. This has been the Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.